This is a production of Cornell University.
And first off today, live from Mexico, we're going to have Margaret Krause, and she's going to tell us about leveraging aerial high-throughput phenotyping for improved early generation selection in wheat. Take it away.
Okay, thank you so much to the organizers for setting this up today on Zoom. To start off, giving a little background on aerial high-throughput phenotyping. This relies heavily on the concept of light reflected off of the crop canopy, and recent developments in the remote sensing, imaging, and aerospace industries have given us a wide range of technologies to use to acquire these phenotypes. And we're using quite a number of them here at Summit to look at different problems in plant breeding and genetics. But today I will just be focusing on unmanned aerial systems, or UASs, as well as multispectral sensors, which give us reflectance at a small number of wavelengths in the light spectrum. In our case, we get 5. And from this information, we can calculate what are called vegetation indices. It's been well characterized in the literature that vegetation indices can be useful proxies for things like overall plant health, response to stress, changes in phenology, etc. So we're interested in those for potentially using them to select at the early stage in wheat. I am calculating and working with quite a number of them, but for this presentation, I'll just be working with NDVI, which is a ratio of reflectance in the near infrared and red regions of the spectrum. So a little bit of background on the Summit breeding program. Some of you might be familiar with their method of selected bulking. So plants are selected in bulk between the F2 and F5 generations, and the F6 is really the first time when they're selected and harvested individually. And then they're planted in small 2-row plots that are 1 meter in length, and these are unreplicated. A couple weeks ago, we just finished hand planting 38,000 of them, so it's a lot of work. And we could theoretically measure grain yield at this stage, but trait heritability is low and not reliable for selection. In addition, we don't really have the machine or manpower to harvest and weigh that many samples. So at this stage, we're still working with visual selection, and then those lines move on into the first year of replicated yield trials. It could potentially be beneficial to have accurate predictions of grain yield at the F7 small plot stage, and that's what we're trying to look at with aerial phenotyping. So we've kind of designed an experiment to ask this question: can we use phenotyping to select at the early generation stage? And we designed the experiment so that it would be kind of integrated into the breeding program and not use a lot of extra resources. So the breeders went through the F7 small plots in 2016 to select lines to move on into the large replicated yield trials in 2017. We went through and selected a subset of those 1,080 lines and planted them again as unreplicated 1 meter small plots. So these lines were planted twice in 2016, both as small plots and as large yield plots. We used a Matrice 100 UAS by DJI equipped with a MicaSense Red Edge multispectral sensor to phenotype the plots at multiple time points during the growing season. We also assessed yield in both the small and large plots. Again, we don't normally assess yield in the small plots, but we did so this year for the purpose of this experiment. I want to take you guys through some of the steps of the aerial phenotyping and imaging pipeline that we use at Summit, because there are a lot of considerations that we have to get right in order to get usable phenotypes out at the end. Before we can even fly, there are a few things to do, and one of those things is to make and place ground control points in the field. These need to stay in one place throughout the growing season, and they need to be visible to the sensor. Once we've collected their RTK GPS coordinates with our RTK system, we can use that information to assign physical locations to each of the images, which is critical to being able to stitch them together. We also need to create a flight plan for the UAS, and we do that in a software called Mission Planner. Again, in order to stitch the images, they have to have sufficient overlap. So we shoot for 80% overlap and 75% side lap, and we can program that into the flight plan. The altitude speed of the UAS and capture rate of the sensor can also affect the overall quality of the image. And we fly the MicaSense at 30 meters at 12 kilometers per hour, and the sensor has a capture rate of 1 image per second. On the day of the flight, there's a lot of things to remember to bring out to the field. Batteries are actually a big bottleneck for us. We bring out multiple SD cards for the images and a computer to store them on at the end. We run an app on a tablet that will control the UAV, and it runs the flight plan mostly automatically. So there's very little manual control of the UAS that's needed. Before every takeoff, we also take images of a calibration panel. Calibrating the images is really important because atmospheric conditions on the day of the flight can affect the amount of light that's captured by the sensor. So what we do is we measure the true values of the calibration panel with a spectroradiometer and then compare those to values taken on the day of the flight and create a model that will calibrate all of the images prior to stitching. This is really important if you want to compare phenotypes on different dates and track growth throughout the growing season. We stitch all the images together using a software called Pix4D, and the composite image that comes out is called an Ortho mosaic. I put up our Ortho mosaic of the small plots area from one time point, and I've taken out a section for you to see up close what it looks like. That little white thing in there is a ground control point. Our final resolution is 1 to 2 centimeters per pixel, so it's pretty good. Again, these are the 1 meter plots, so they're fairly small. To extract the data, we use ArcGIS, and first thing, we create a soil vegetation mask using a maximum likelihood classification. So this will assign a binary value to pixels that are either soil or vegetation. We can apply that mask back to the original image and remove any data associated with soil. And then the last step is to draw polygons around the plots and calculate plot level statistics on the data bound by the polygon. So there are a lot of considerations that go into this, and hopefully if you do it right, you can get good quality results, and that's what we think we're starting to see here. In both the small and the large plots, we had higher heritability for all of our NDVI time points than we did for yield, so that's promising. In terms of yield, we had a correlation of 0.3 between the small and large plots. That's about what we expected. And in both experiments, we saw significant correlations between NDVI and yield. It was a little bit greater in the large plots due to their size. The relationship that we're really interested in, however, is between small plot NDVI and large plot yield. And here we're seeing that it's 0.43, so that's pretty good. I looked at this in terms of correlated response to selection. So in this case, the correlated trait is actually large plot yield, and we could theoretically select off of small plot NDVI or small plot yield. And we're seeing that the NDVI is twice as effective. The reason for this is because it has higher heritability and it has a higher correlation with large plot yield than small plot yield. So these are looking promising as a selection tool. I also did some multi-trait genomic prediction work, and this is work sort of following Jessica's initial work using HTP traits as secondary traits in GS. And the setup that I use is a little bit complicated, so I wanted to go through it. The training set that I used was 80% of the lines. The target trait was large plot yield, and the secondary trait was large plot NDVI. So we fit this model using pedigrees. And then for the test set, we used the remaining 20% of lines. Yield was hidden this time, and small plot NDVI was actually the secondary trait. So the predictions that we got out, we correlated back to large plot yield. So the idea of doing this is you could fit a model using the large plots where you have both yield and NDVI available, and then use it to predict the small plots where you only have NDVI. And assess what their yield would be as if they were planted as large plots. So I've plotted the results along the bottom in white, and we're looking at multiple time points for the NDVI. So I tried to show where those are in relation to the phenology of the trials. That's what the top two graphs are. CIMMYT has a huge aerial phenotyping program. I think we did more aerial phenotyping last season than any CG center has ever done. We have a lot of different experiments going on, so unfortunately those things, as well as changes in the weather and responsibilities in the field, prevented us from phenotyping both trials on the same date. We also had a lot more phenotyping dates that we had assessed, but several of them didn't make it through our quality control pipeline. So these are the dates that we have. We have 2 in the small plots and 4 in the large plots. You can see in the results that adding NDVI as a secondary trait doesn't improve over the univariate case in most cases, but it does so twice, most notably when both the small and large plots were phenotyped on March 13th. We know that NDVI is sensitive to phenology. So this coming season, we will be paying a lot more attention to trying to phenotype these trials at the same time. We got them planted on the exact same date this year, so that's really good. We just want to make sure that we're doing our best so that we're not comparing apples to oranges. One more thing I want to say about this is in this experiment, the training set and the test set were assessed within the same breeding cycle. But if we were to do this in practice, the training and test sets would be 1 to 2 breeding cycles removed. So it's possible that what we're seeing here is a little bit of within cycle cross-validation bias, which is characterized in the literature, and that NDVI could actually be more beneficial than what we're seeing, but we have not assessed that yet. So some quick take-home messages. The small plot aerial NDVI traits tend to be more heritable than yield. They are predictive of yield in the large plots, and their correlated response is twice as effective as the small plot yield. With our multi-trait GS, NDVI does have the potential to improve accuracy, but timing around the phenology appears to be really important, and we will be taking steps to improve that this coming year. So that's what I have for you guys today, and I'd like to thank my committee, especially my advisors, Mark and Mike. At CIMMYT, I'm working with Dr. Jose Krause, who's in biometrics, but as you can see from the photos, there are a lot of other people who help make this phenotyping possible. This project has also been heavily supported by Kansas State. Jesse has been co-advising the project. His UAS technician, Rich Brown, who's pictured there, taught me how to fly, and Atina has been helping with some of the image processing. And of course, I wouldn't be in Mexico without my funding sources. So thank you to USAID and their US Borlaug Fellows and Global Food Security Grant, as well as the National Science Foundation grant. So I'm happy to interact with you guys for a couple minutes if we still have time. So thanks again to the organizers.
Thanks, Margaret. Questions?
You should repeat the question if she won't be able to see.
Yeah, or I could run the mic too. Yeah, Tier.
Can you hear me, Margaret? Sounds
Sorry.
So down in Obregat, when you're taking NDVI images, is the lack of greenness and that kind of, being robust versus not robust, healthy versus not healthy, is that drought, heat, nitrogen stress, all 3 of them, other things? I mean, like what fundamentally is the, I guess, what is the stress tolerance or stress resistance or whatnot that is being reflected in NDVI? What are you selecting on, in terms of that?
Yeah, so in terms of that, for this particular experiment, it's probably just going to be a lot to do with biomass in the small plots, germination, things like that. But we are using these technologies at CIMMYT in our other environments. And so we have a drought experiment, we have a heat experiment. And in those experiments, we see a lot of difference, a lot more variation in NDVI that would be linked to those things.
Margaret, this is Dan. Could you flip back a couple of slides to the prediction accuracies on the... Yeah, so on March 13th, do you think the high prediction accuracy there is an artifact of being scored on the same day in large and small plots? Because it's just kind of an arbitrary time in grain fill, or do you think that's actually legitimate?
So what we've been seeing is that the time points that tend to be the most predictive in our program tend to be during grain filling. And we haven't necessarily focused all of our phenotyping efforts to just focus on the grain fill stage, because I think the breeders are interested in having phenotypes from earlier in the season Certainly it takes time to process the imagery, so to have phenotypes in the hands of the breeders at the time that they're going through selections, you might have to start earlier. So that's something that it'll be interesting to see what the results come out as next season, if it's only grain filling that is the time when we can phenotype effectively.
Well, if there's no more questions, let's all thank Margaret.
This has been a production of Cornell University, on the web at cornell.edu.